Hello, today's lecture is about gradients. In this lecture, we will explain three types of gradients. We have the uniform or pure gradient, arithmetic gradient, and geometric gradient. Now, in general, the term gradient means that when you see in your cash flow diagram that the amounts are changing by a fixed or a constant value each period, then we have a gradient. The first type, as we said, is the uniform gradient, such as this case. When you look at period 1, not 0, at period 0 we have nothing in the gradient. And in the case of pure gradient, at period 1 we have no cash flow. It is 0. So the gradient will start to appear at period 2. Now at period 2, the amounts will start with G. At period 3, you will see it is 2G. At period 4, it is 3G. So you notice that the amounts are increasing by a value of G. So when at period 2, you notice that the first amount begins with a G and continues to be increased or decreased with this G, then you have to know that this is the case of pure or uniform gradient. Now we can get the equivalence of this gradient as we used to do using the equation or the table of interests. So we can get the present equivalence of any gradient using this equation or by using this factor P equals to G into P knowing GIN. Similarly, we can get the annual equivalence to the gradient using this equation or the future of any gradient using this equation, but it's easier for you to use the table of interest where you get the value from the column without getting to fill in values in big equations. Let's see an exercise together to understand the idea more. Suppose that at the end of year cash flows are expected to be 1,000 for year 2. You see, I have no amounts at year 1. So this is a clue to tell you that this is the case of pure gradient. Now, 2,000 for third year. You see, what's the amount that is added? I added $1,000, which is the same as the value that we began with it at year 2. This is another proof. Then I continue by increasing the amounts by $1,000 each year. So all these things will indicate that this is the case of pure gradient. What do I need to get? Find the present equivalent value and the uniform annual equivalent value. Let's begin first by looking at the table of interest to see where will the values be. Now you see these two columns were related to single payments. These four were related to annuities, uniform series of payments. And the last two columns in the table are related to uniform gradient. I can find P given G and I can find A given G. Now, going back to our exercise, the first step is always beginning by drawing the cash flow diagram. At year 0, I have nothing. At year 1, I have nothing. And the first payment will start at year 2 with the value of G. So G was $1,000. The next amount was 2,000, 3,000. So I just can draw a line indicating that the amounts will increase by a value of G, which is 1,000. I began with 1,000, 2,000, and 3,000 as the given states. So I know that G equals 1,000. If I want to get the present equivalence of this amount, you just directly apply the equation. P equals G into P knowing GIN. Now G is the 1,000. The interest here was 15%. And N equals to 4. Why 4? Because having the 0 at year 1 is part of this gradient. So you do not just say that I have 3 payments. It's not the same as the annuity. So you will have to say the last payment was at year 4. So from 4 to 0, I have 4 years. Okay? Because we will include this year 1 even if the amount paid or gained is 0. It is included in the calculation. So please pay attention to this point. Now we just put the value from the table looking at the column related to P knowing G, and this is the present value. What if I want to get the annual value of this G? So you say A equals to G into A knowing G I N. Again, you will always say that the value of N is 4 because the last arrow ended at year 4. So you will consider that it's a 4-year period always. Or if you want, you can get benefit of part A, where I already got P0. So if you know P0, can't you get its equivalence, annual equivalence? So you will say A equals P into A knowing P IN, and you will be getting the same answer. You see, that's why I keep telling you that there's no single method of solution. Now, sometimes we get to work with combinations, meaning that we are dealing with a pure gradient, okay, and an arithmetic gradient, where we have an annuity plus the gradient. So in this case, or in this situation, we might be dealing with two possibilities. Okay, so this is the case where I have annuity and a gradient at the same time in my cash flow diagram. This gradient can be something that, or the amount that keeps being added, or it's being increasing. For example, 1,000 at year 2, it will become 2,000, 3,000. 1,000 at year 2, it will become 2,000 at year 3, and so on. The amount keeps increasing by 1,000. Sometimes we face another possibility, is that the gradient's amount is decreasing by 1,000. Okay, so we have two possibilities. Let's see how will it look like. If you look at this cash flow diagram, you will notice that we already have a G beginning at period 2, and the amount is being increased by a value of G each time. So this is the case of pure gradient. And at the same time, you notice that we have an annuity that is taking place at year 1 and continuing till year N. So when you look at the cash flow diagram and you see that we do not have the case of pure gradient, but we have a pure gradient plus an annuity, then this is referred to as the arithmetic gradient, and this is the second type of the gradients that we will discuss. The arithmetic gradient will look like this. You will notice that we have a starting point at year 1, we have an annuity. Then at year 2, we will see that this amount that I got here will start to increase by a G, then 2G, then 3G. So if we want to split this cash flow diagram, we can see that it can be split into an annuity plus a pure gradient. Uniform series meaning annuity, and the pure gradient. So when I have this combination, this is the arithmetic gradient. Now I can get the present worth of this arithmetic gradient, or I can get the annuity of it. How do I do it? The first thing to do is to split it into two parts and then get the present worth of this part, the present worth of this part, and add it together. Let's look at this exercise. Here at the end of year 1, we have an amount of minus 400. Now this minus just is an indication of the direction of the arrow. It means that this is an amount that's going to be paid. And if you look at the amounts, you will see that the first amount was 400, the second one was 450, 500, 550, 600. So the amount is being increased by 50. So right away you can say that the gradient here is 50. It is an increasing gradient because the amount is increasing each time. However, if I was beginning with 400 and the amount was 350, then 300, then 250, then I would say that this is a decreasing gradient. And when the gradient is decreasing, you just have to put a minus sign before it. Now, this is not related to the minus sign that you see here. This minus sign just to tell you that we have a payment at year 1. We have a payment at year 2 of 450, just to indicate the direction of the arrow. The cash flow diagram will look like this. At year 1, 400, 450, 500, and so on. So what do you notice here? Is it the case of pure gradient? Is the amount that you see here, 450, is the added amount? So the next amount is 900, and then add another 450 and so on? No, because we agreed the gradient is only 50. Okay, so since this is not the case of pure gradient and we already have an amount at year 1, I will refer to it as the base amount of 400. Then I can say that I have an annuity of 400 that will continue from year 1 till 5, and I'm adding a gradient of 50 to this base amount of 400. So here you know that this is a typical arithmetic gradient cash flow. So in order to get the present worth of this cash flow diagram, we'll split it into 2 parts. We will have a base amount of 400. Always the first amount that you see at year 1 will be your base amount. So this will be your annuity. So an annuity of 400 plus 0 at year 1. Because I'm splitting this table into 2, this cash flow diagram into 2. So at year 1, what do I have? Only 400. So as if I'm saying we have 400 plus 0. This 450, it is 400 plus 50. This 500, it is 400 plus 100. Okay? So you will notice that at year 1, I have 0. And at year 2, I have 50, and then the amount keeps being added by a 50. So we have this as the pure gradient case where G equals to 50 and the amount continues to be added by a 50. So if I want to get the present worth, I will get the present worth of this annuity. So the total present worth will be, or the present equivalence will be the present value of the annuity plus the present value of the gradient. You have to look at this sign. Is it an increasing amount? Is the gradient being added? Is the amount here, it's 450. Is the amount becoming 400 or is it becoming 500? It's becoming 500. So this means that the gradient is being increased. It's amount added. So that's why the sign here has to be plus. But if this amount was 400, then it became 350 and 300, then this is a decreasing gradient of 50. So just change the sign here. We only change the sign here to become negative in the case of a decreasing gradient, but the rest of the calculations remain the same. So looking back at this cash flow diagram, I want to get the present of this gradient. So PG equals to G, the gradient. P equals G into P, knowing G-I-N. And what's the number of period? We agreed that we will have to be looking at the last arrow. It occurs at year 5, so we have a total of 5 years. So we put 5 here and 5 here related to the annuity. Let's look at another example. Here at the end of year 1, I have 2,000. At the end of year 2, I have 3,000, 4,000, and 5,000. So what do we notice? I notice that G equals to 1,000. But do I have an amount at year 1? Yes. So this is your base amount. So I have an annuity of 2,000 and I have a gradient of 1,000. So this is the case again of an arithmetic gradient. But this time I don't want you to get the present worth of this cash flow diagram. I want to get the annuity of this cash flow diagram. So once again, we will be splitting it into 2 parts. Annuity of 2,000 and the pure gradient that has 0 at year 1 and 1,000 at year 2 and so on. So what will be the annuity of this cash flow diagram alone and the annuity of this cash flow diagram alone, and then I will add it. What is the annuity of this annuity of 2000? It is already annuity. So you say the total annuity is 2000 plus. Now what's the annuity of this pure gradient? I have G of 1000. What is the annuity of it? A equals G into A knowing G, I 4. So you just add this part with this part and you can get the annuity. So in case of arithmetic gradient, you can calculate the present equivalence of it or the annual equivalence of it easily by direct application, as we saw. Now let's consider a case of a decreasing gradient. In this example, we have a couple who wants to save for their daughter's college expenses. The daughter will enter college 8 years from now. She will need 43,000, 42,000, 41,000. You see the amount is being decreased by 1,000 for the 4 school years. Assume that these payments will begin at the end of year 8. How much the couple must save each year? So I'm asking what? This is the key word, save each year. So the annuity till the end of year 7 at an interest rate of 10%. The first step is to draw the cash flow diagram. So the couples are saving each year till year 7, till the end of year 7. So this is annuity, okay? So that when the daughter enters college at year 8, she will be able to withdraw these amounts that are being decreased by 1,000. So here I want to calculate the annuity. Now, again, this is a gradient, right? Now this is a gradient where I have a base amount and a decreasing gradient. Where is the present value of this gradient? This is, we will say that the first payment here, it's happening at year 8. This is the annuity. This is the base amount. And then we will split the rest into an annuity of a base amount, and it's being decreased by a gradient. Now, where would be the present value of this gradient? It will be the previous period, because here where the first amount took place. So the present value of this gradient and annuity as well is at year 7. So again, when we agreed last time that whatever you're gonna save will allow you to make these withdrawals, so these are equivalent. Where do you want to make this equivalent take place? You can equate at the future or at the present, but it's most convenient to equate at year 7, where the present value of these payments is already at year 7 and the future value of all the annuities is already at year 7 at the last payment. So considering this side, I will be getting the equivalence at year 7, so as if I'm getting the present value. So what will be the present value at year 7 related to the gradient? I will be splitting it into an annuity, so P equals A into P knowing AIN. What's the number of periods? 1, 2, 3, and 4. And the annuity is 43. So 43,000, this is your base amount. Always begin with the base amount. Now, we have the second part related to the G, pure gradient. What's the value of G? It is 1,000. So the present value is P equal G into P known G, I4. You see, because this is a decreasing gradient, the only thing that I change is this sign, okay? Don't change anything else, because this exercise already came in the final exam last year, and students, what did they do? They said that they will begin from 40 and they will increase a gradient of 1,000. However, this is wrong, because always you will have to begin from the base amount, the first amount that you see. Whether the gradient is increasing or decreasing, you can change this from the sign here. That's it. Okay, so I got the present value at year 7. Okay, so this is the resultant. Can't I say that this present value at year 7 is equivalent to the annuity occurring from year 0 to 7? So you just say annuity equals to P7 into A knowing F. Why A knowing F? Because when you get the present at year 7, you will be, this reference point will be here. You will be stopping here. Now, this, with respect to the annuity that you have, is what? It's the future. So I'm getting the annuity of the future at year 7. So annuity will be A equal F into A knowing F, I7. And my F in this case was the P7 that I already calculated. So you get the annuity. Okay? Or as we said, you will just get the values here as P7, and you get the future of this annuity equated here. Put this side equal to this side, so basically it's the same calculation. It will give you the same answer. Now the last type of gradients is the geometric gradient. It's the case when you see that the amount is increasing or decreasing by a percentage. Okay, such as the salary, where it will be increasing, let's say, by 20% each year. So it's not a fixed amount, it is a percentage. So when this is the case, look here, 1000, 1200, 1044, it's not being added by a fixed value, it is a percentage. So when this is the case, and you want to get the present value, you will be using this equation only, where P is the present value, A is the annuity, G is the rate of change. Yani I'm adding my salary by 20%, so G will be 20%. I will be the interest rate. Okay? Now, we have a special case. If G, the percentage of increase, is equal to I, the interest rate, in this case, we will substitute this equation by P equals A multiplied by N over 1 plus I. Let's see an example. Here we have a contractor trying to calculate the present worth of personnel salaries over the next 5 years. The combined salaries of his employees is $150,000. If he expects to give his employees a raise of 5% each year, the present worth at 12% is how much? So I is 12% and G is 5%. This is the raise. Okay, and 150 is the annuity, and I need to calculate the present worth. So applying the equation, P equals A, this is A, into 1 minus 1 plus G, okay, over 1 plus I, all to the power N, okay, 5 years period. Now the mistakes that students do when they see this equation, they will forget that all of this bracket is to the power N. So 1 plus G is to the power N and 1 plus I to the power N. That's why I splitted it here, just to make sure, because I see this mistake all the time. And this will be the present worth of this geometric gradient. This is all you need to know about the types of gradients. Thank you for listening.